So in this video, we're continuing with half-lives sections 4.5.4 and 5.5. We're going to start by looking at how to use half-life in problem solving. So you have to look at what's given, what do you need, and what's the plan to calculate that unknown quantity, and then any conversion factors that you can use, and then set up and solve that problem for the unknown quantity. Okay, so here in this problem, you have strontium 90 having a half-life of 38.1 years. If the sample had 36 milligram, how many milligrams will remain after 152.4 years? Okay, so the half-life is 38.1. You've been given that the time elapsed is 152.4. So if you divide this 152.4 by 38.1, you should get the number of half-lives, because each half-life is 38.1. All right. And then once you have that, then you can determine, because each half-life, with each half-life, this is going to become half its original. All right. So you're going to write a plan how to determine the number of half-lives, because one half-life is 38.1 years, and you can write that as a conversion factor. So 152.4 divided by the 38.1 gives you 4 half-lives. All right. So you started out with 36. So after one half-life becomes 18, after the second 9, after the third 4.5, and then after the fourth around approximately 2.3 milligrams. Another way to do this more accurately and faster is to use this formula. So here nt is equal to n0 times half raised to the power of n, where nt is that final isotope mass, the initial mass given, and n is equal to the number of half-lives. All right, so you can take that same 36 milligram, that was the initial mass. The number of half-lives we determined was 4, so half raised to 4. All right, and then when you do the math here, you would end up getting 2.3 milligram. All right, so I think this is a faster way to do that compared to the other method, but both work. All right, so carbon-14 is used to determine the age of the Dead Sea Scrolls, which were 2,000 years old. And so this is, carbon-14 has been instrumental in dating a lot of archaeological finds, especially biblical finds, and place them in context and history based on the carbon dating data that was obtained from the analysis of the carbon-14 dating. So carbon-14 was used to determine the age of the Dead Sea Scrolls. If the scrolls were determined to be 2,000 years old, and then the half-life of carbon is 5,730 years, what fraction of this half-life has passed? All right, so approximately 2,000 years has elapsed. The half-life is 5,730. All right, so how much of that fraction of half-life? All right, so one half-life is 5,730. That's your conversion factor. So 2,000 divided by 5,730 gives you 0.3. All right, so that 2,000 years elapse is 0.3 of a half-life. Okay. The half-life of iodine 123 is 13 hours. How much of a 64-gram sample is left after 26 hours? So 26 hours, that's 2 half-lives. So substitute that into that formula. Nt is equal to n0 half raised to the power of 2. So you start out with 64. Half is 0.5 raised to the power of 2, which is 2 half-lives, and then determine what that answer is. And that's 16 milligrams. So scanner is used to detect radiation once the patient has consumed the radioisotope, either it's been injected or it's been taken orally, and then the scan of the thyroid will show if there is any kind of imbalance or some kind of medical condition that needs to be treated. So you do need radioisotopes with very short half-lives that can be used so that they don't stay in the body for too long and cause additional destruction. All right, because in the body the cells are not differentiating between the iodine which is not radioactive from the iodine which is radioactive. All right, so once those thyroid cells have taken up that iodine, then what happens is the presence of the radioactive iodines are detected because they're emitting radiation from those cells, and then you image the thyroid organ after that. So some of these radioisotopes and what they used for, what type of source of radiation, what's their half-life, and as you can see, most of them have very short half-lives. And then most of them are very specific, like fluorine, for example, is used in positron emission tomography, iodine for the treatment of thyroid related diseases and diagnosis as well. Phosphorus is used in the treatment of leukemia, etc. And then so most of them have like these specific areas in which they accumulate, etc., or they are taken up by. All right. Whereas when it comes to technetium-99 metastable, it's able to use to diagnose a lot of different parts of the body, like the skeleton, muscle, brain. So it's the most widely used radioisotope in nuclear medicine. So after the radioisotope is ingested, then the radiation starts getting emitted out of the body. The scanner moves over that organ where that radioisotope was taken up by, which organ it was taken up by, and from which the radiation is being emitted, and then the radiologist will then determine the level and the location of the radioactivity, and then that is then exposed to either a photographic plate or a scan, and with the help of a computer then this scan is looked at. So here is a scan of I-131 taken up by the thyroid, and positron emission tomography, PET, as it's as the acronym is given for it. Positron emitters have short half-lives, and they're used to study brain function, metabolism, blood flow. So carbon 11, oxygen 15, nitrogen 13, fluorine 18. What happens is they combine with the electrons after emission, and they produce gamma rays, and then that's detected, and then a 3D image of that organ from which they're being emitted is created. So this is the PET scans of a normal brain on the left, and then the Alzheimer's, a person with Alzheimer's disease on the right, and you can see that the blood flow areas are different in a normal person as opposed to a person with Alzheimer's. All right, so this is a CT scan, computed tomography, and it's used to scan organs like brain, lungs, heart, and then so the differences in absorption of the X-rays based on the tissue densities and fluids, etc., provides a scan of this brain, and it shows wherever there's a dense tumor, like here, and then we are able to detect brain tumors, etc., with this method of imaging. Magnetic resonance imaging doesn't really involve any kind of radiation, all right? So it's least invasive because it's not radiation. It doesn't involve radiation, all right? But it does involve absorption of energy, and this is from protons, because 60% of our body is made up of water, and so in a strong magnetic field, those protons get lined up a certain way with respect to the magnet, and because of that, that energy absorbed can be converted into images. So this is an MRI of heart and lungs, showing the blood flow. So in this study check, it says, which of the following radioisotopes are most likely to be used in nuclear medicine? So this has a half-life. Potassium-40 has a half-life of 1.3 times 10 power 9, and that's too long, so no. Potassium-42, half-life of 12, and iodine-131, half-life of 8. So both B and C are viable to be used in nuclear medicine. Brachytherapy. So this is where a seed is implanted in that affected organ, such as in the treatment of prostate cancer. So these seeds are tiny little titanium capsules. So in that area, the malignant area where the cancer is, they're implanted. This way it's a pinpointed radiation, because what happens in radiation otherwise is that even the healthy cells can get damaged, can undergo tissue damage, all right? So to minimize the tissue damage by the healthy cells surrounding the cancerous cells, this pinpoint radiation helps in only getting rid of the cancer cells, all right? So that's called as brachytherapy, okay? So iodine 125, palladium 103, and cesium 131 in these seeds, and the emission is gamma emission, and that will destroy the cancer without affecting the other cells, the normal cells around it. So temporary brachytherapy, it involves implantation with long needles containing iridium-192 into the tumor itself, all right? So you're delivering a high dose of radiation, but over a very short time, and then it's repeated every few days, all right? So that way, again, you're pinpointing the radiation to just the tumor cells. All right, the homework for this chapter is 5.1 to 5.12 on page 155, 5.13 through 5.22 on page 162, 5.23 to 5.28 on page 165, and 5.29 through 5.34 on page 169, and 5.49 to 5.75 on pages 178, 179, and 180. And that's the end of chapter 5.